minimum to vote.
I knew it would.
Is it still smelling?
Well, let me talk about some other things before I start the lecture. Is by lunchtime or so, I'm going to start taking total. You telling me exactly which ones of the 8 experiments you guys are through with, and that's where I might give you 20 questions to see if you really did it. I'm going to spend a little more time. I got both TDRs up and running, and these are the fanciest, schmanciest things I've ever seen. Ergo, also not so easy to use. But they're also the fastest one. They're like 10 picosecond rise time with incredible resolution. And they have 4 channels, which basically makes this a 4-channel time domain network analyzer. And so it has an incredible amount of capacity. Normally we just get a TDR or a TDT, but this thing is a 4-channel TD, TR, TDR. It can just do a lot of stuff. So it has 2 modes on it, and one of them is, quote, the simple mode, but then they give us another one of these expensive calibrator boxes, which I'm finding out is not so straightforward to use, but I'm halfway through figuring it out. At the very least, we will do this box in the simple mode. But it has a new kind of connector which I have never used before either, and there are 4 adaptoids inside the cal box here which are essential. But this is essentially an APC, probably a 2-point-something millimeter connector. And so the only thing that will make this box work are the connectors inside these cal kits. So again, once we use them, we want to just keep everything very straightforward as to which one is which. Okay, so this is going to be the last talk. I had another one on vector signal analyzer, but I don't know that it's necessary that we go through that since you have been playing on a number of these boxes already, and many of them now look like swept spectrum analyzers. In the early days, a vector signal analyzer was a slightly different beast, but they realized that people who know spectrum analysis like the same buttons and same terms on their vector signal analyzers. So they've almost become transparent to each other. All right, today's talk is then going to be about a whole system design. So everything you've heard so far is about the little bits and pieces, whether it be cavities, components, transmission lines, use of the devices needed to measure or calibrate all of these devices. At some point, if you're continuing to work in an accelerator environment or even in a commercial environment where you need to build and put together block diagrams, put together systems for potentially accelerating beams, this is an overall simplistic review of everything. So many of you are already in the accelerator business and know that if I have a force of 1.5 volts and I put it across a gap, I can impart energy to a charged particle of 1.5 electron volts. So that's one of the very simplest things. And of course, the way we do it is not with batteries, but we do have the vacuum tube so that the particles don't crash into other residual gas particles, and therefore would not have much chance of either going in a straight line or a circle. Okay. And the way we accelerate particles conventionally is with RF waves. Now, of course, there's lots of effort working with plasma wake field acceleration, and those are waves of another kind where an incident beam goes through a plasma and creates an electric field wave where the following chase beam comes through and sees a very high electric field and gets accelerated. There have been successful tests of doing that, but on a onesie basis, not putting many of these types of wake field devices in series. And then, of course, the issue of recovery time of the plasma, because once the beam goes through, you can just imagine it like a bullet going through jump. It sits there and it sloshes, and eventually has to come back to equilibrium before you can put the next pulse through it. But we're going to be doing with RF waves, and we can of course only accelerate charged particles. In this case, it's Mr. Proton here on the wave. And I showed this picture the other day there, but the thing that's very important when you're trying to accelerate a charged particle is the synchrony of the particle with respect to the electric force that's propelling it to higher energies and changing the momentum of the particle. So I don't know that anybody around here is a surfer, but we've seen surfing on television at the very least, and this guy is at a very good synchronous phase with this wave. If he were to end up starting to go up a little bit, of course, then the acceleration would increase, and he'd probably come down, and the acceleration would decrease, and he would be basically bouncing back and forth, up and down on this wave in a synchrotron motion, okay, just like a particle would. And of course, this guy's got to be traveling at the right group velocity, because if he stays perfectly still, all of this stuff behind him is going to come crashing in on him, and he won't be going forward too much anymore. So surfers certainly understand synchronous phase, and they can execute the same kind of particle motions on a surfing wave as a particle does sitting inside an accelerator. Okay, so we're going to start talking about the building blocks of now trying to build an accelerator RF system. So Dave was talking about the development of cavities. This is a very rudimentary storage device. It's a capacitor inductor in parallel, and it makes in the resonant circuit. And schematically, that can be shown as this, where we know that the resonant frequency in radians is 2 pi of 0, which is the square root, reciprocal square root of the inductance times the capacitance. This you should have had someplace in Physics 101 or 107 or whatever you had. Okay, well now we can look at it schematically and start to transform it into something that would look like this. And the inductance now in an actual cavity is typically whatever metal you have that brings the outside of the vacuum vessel back around to some kind of a capacitive gap, which is always where the nose cones could be, right? And eventually you could transform this into many different shapes. And Dave talked about how the R over Q of the cavity is a function of its geometry. Now this cavity is starting to look a little bit now like maybe a superconducting cavity. This is a 3.9 gigahertz superconducting cavity. And of course, if you put a hole through the middle to allow the beam go through, then the beam can experience the accelerating force that's created, we'll do better, just in like, they're created across this gap. And depending on the material you use it, the temperature it's at, that'll control how much losses there are in the cavity. And we already know that the Q is a measure of how good the cavity is. It's a quality factor. The less loss I have, then the more shunt impedance I have across that gap, and a fixed amount of power will create a larger number of volts in a high impedance cavity, and that's of course the force that makes the particles move. Okay, but of course no cavity is perfect. Even superconducting cavities have got a certain amount of residual impedance, and so you have this shunt impedance across any kind of cavity you could possibly make. The difference being in a low frequency cavity, well, this cavity is 805 megahertz. Some of you have started to measure it. And it has the one on that table at least has about a Q of about 700. It's made out of aluminum, but the two clam helves are just held together. There's pins to align it, and there's that band clamp on there to just hold it together. If that was brazed together, as a real cavity would be, made out of aluminum, that might jump up from 600 to 10,000. The real ones that we have at Fermilab look just like this, and they're made out of very high quality copper, and they're brazed and degassed, etc. Those have Qs of about 20,000. Copper cavities can easily have Qs of between 10,000 and 50,000. We just built a cavity for the mice experiment that'll take place in RAL in England, and it has a loaded Q of 50,000. It's big. It's about, I can show a picture of that. It's a big thing, and it's driven with 2 couplers, which is a little tricky. We're going to talk about coupling with 2 couplers, but it's one way. You can always use a cavity as a combiner too, is if you have to put a real lot of power into a cavity, the device that delivers the power to the cavity may not be able to sustain the high voltage on the coupler if you had to put it all through one spigot. So you can actually pump a cavity from multiple ports But then, of course, you have to be very careful at the phasing so that the electric fields add up instead of try to cancel each other. So everything has to be perfectly balanced. And the way you make something perfectly balanced is you have to have some kind of a splitting device that has absolutely excellent amplitude balance and excellent phase balance, and then you cut all the coaxial cables to the exact same length so that when you deliver it to the cavity, you get the power delivered to each cavity equally. And then, as you will see, how many people have done the cavity experiment so far? You guys, just you guys so far. So you'll see when you're over there that one of the input couplers is a loop, which couples to the magnetic field. And many cavities use this technique because it allows you to tune the coupling value by just rotating the loop that's at the end of the coupler with respect to the volume of the cavity, and it couples in a variable amount of flux to the cavity and actually tunes it so that you're in resonance with your 50 ohm input and whatever shunt impedance it transforms you to. So you'll see that that's the capability of doing that. And sometimes you split couplers up just because you have so much power you want to put in there to get a very large voltage across the gap. Okay, so we talked about what Q is. It's always on here. And it's the energy stored versus energy lost per cycle. And you want that, the whole bottom line is if you want to accelerate a particle beam, you want volts. Volts is the force that pushes the charge. But how do you get volts from power? Well, it's a transformer ratio. Is if I have a fixed amount of power and I put it into a low impedance, I don't get many volts. So I really want to go to a high impedance, and then one way of doing that at low frequencies is with a transformer. And a cavity is essentially a transformer. It takes whatever your drive impedance is, which could be, if you had a tetrode or a triode physically right on the cavity itself, and it's relatively high power, tens of kilowatts or 100 kilowatts, you can do the impedance calculations. A tetrode or a triode may have an impedance of 100 ohms. It may have an impedance of 300 ohms, 500 ohms. It may have an impedance that's closer to 50 ohms. It depends on the voltage current ratio that you have across the anode of the device that's driving the cavity. And so you need a matching network. Where do we did matching networks? We learned how to do matching networks right here. And the matching network is such that I have to go from my driver into the cavity. Now, the cavity can be far away from the driver, as was the case in the Tevatron. The Tevatron, the cavities are 30 feet below ground. The power amplifier was upstairs. The reason for that was access to fix it. But then we used a 9-inch coaxial line to get the energy down to the cavities. And that was maybe, because it was going on a diagonal, those were maybe 40, 50 feet long. So I have an amplifier now that may have several hundred ohm impedance, which needs a matching network to get to the 50 ohm transmission line. And then at the input of the 50 ohm transmission line, it goes to a coupler to the cavity, and that coupler to the cavity transforms it up to the high impedance that's across the gap. And so there's a situation where you have an amplifier, which you need to design, measure, and understand, a transmission line, matching networks, couplers, coupler variation, and you've just started. That's just the power part of an RF system. There's more to go. And bandwidth. In the case of a cavity, you may not need that much bandwidth because you want high volts. So cavity systems are typically very narrow. In normal RF systems, as I said, cavity in copper, 20, 30,000 is possible. But when you start getting to superconducting, Qs can get into the million and 10 million. And now you can think the bandwidth, depending on what frequency you're operating at, is no longer kilohertzes or tens of kilohertzes, it's tens of hertzes. And that presents some real issues that we'll talk about. Okay, and bandwidth is information. So if you need for if your system is not an RF system, but maybe it's a damper, okay, and the damper is going to have maybe a need for a much higher bandwidth. So that says your kicker device is not a very high Q. And the only way that you're going to generate a lot of voltage in a lower Q device, because the shunt impedance is lower, is more oomph. And the power is very expensive. And broadband power is more expensive than narrowband power, just because, as you'll see when you start doing matching networks, in order to get a match over a broader range of frequencies, takes more than just a simple matching network. And if anybody here gets to the point where they've got everything down, with the knowledge you have of making a single stub tuner, you can design a 2-stub tuner or a 3-stub tuner, okay, by using the exact same techniques. And what happens there is when you have a Smith chart, and that's another beautiful thing about the Smith chart is how it's intuitive, is, you know, very low Q is right along the real axis. But remember, if I traverse the real axis, then of course I'm going to lose power because I've got resistivity. And you saw as we were doing matching networks, we were going to the unit circle hither and thither. But the further away I get from the real axis, the Q gets higher. And so Q getting higher means less bandwidth. And so a really broadband network will maybe do a lot of zigzags around the real axis, and that's what multiple elements do. And you can actually draw, and I would encourage you to do that, by just looking at the real and imaginary parts of points on here, you can actually draw lines of constant Q, where, you know, there's a Q essentially of 1 on the real axis and a Q of infinity on the outside, and you can draw Qs of 1 and 10 and something like that. And if you're making your matching network, even though you know eventually you want to get to the unit circle, what you've got to do is maybe get there in several steps and don't exceed your Q bandwidth. You're going to end up with a wider bandwidth matching network. And that's what you have to do if you have the need for wideband systems. Problem with that is the more elements I put in my matching network, the more loss there is. And if you're dealing at high powers, that loss is costing you money. So it's always going to be a trade-off for what you need in terms of bandwidth. If you're a single frequency, you want to, and that's what we'll be doing certainly with these cavities here, and also with the mystery boxes. You're just matching at one frequency, but when you're done, you'll open the network analyzer up and see how good it is as a function of frequency. So, like I said, this is going, so far it's going very smoothly. I have been monitoring what everyone's doing, and you're making excellent progress. So all these little extracurricular activities, I think at least some of you will be able to get to them, and of course more light bulbs will go up. I hope. Okay, an easy thing to understand, of course, is at the 45-degree point where the real and imaginary parts are equal, and that's the 45-degree point in the system. That's equal to the 3 dB point. This is how you're going to be measuring the Q0 on these cavities. Under those conditions, that will tell you, you know, what the bandwidth of the cavity is. It's also a good rule of thumb for simple cavities is when we were talking about noise, and when you guys were looking at the noise on the spectrum and everything else, is and seeing the noise floor go up and down, is that you change the resolution bandwidth, your signal should have stayed perfectly fine, but the noise floor should have been going up and down. If you change the resolution bandwidth by a factor of 10, it should have changed by 10 dB, for instance. And that's because the real noise bandwidth of any system is the integral of whatever is underneath that passband. The way things used to be done to be very accurate, certainly when I was even taking it, is you would actually plot what the response was in linear terms, and then there was a very clever device which I think I had one at work. It's called a planimeter, and a planimeter is a really interesting graphical tool that you set it there on the paper, and it's got 2 orthogonal rolling wheels, and when you trace out any curve, no matter what it is, this ingenious thing that's probably been around for 200 years, when you trace around a closed curve, it gives you the area of the curve. And now that you know what your 2 axes are, that tells you the very accurate noise bandwidth. Well, that is very tedious. You may even read that in the Adams book, for instance, that talks about doing that. But generically now, I think if you have a simple cavity without ripples and everything else, that the 3 dB bandwidth can be considered the noise bandwidth as well. But the real bandwidth of a system is the integral of its entire bandwidth for, say, the gain that's above 0 dB. Okay, so of course we don't accelerate with batteries, but we do put the combination of whatever accelerating device you have together with the cavity to generate the acceleration pulse. And back in 1939 at Stanford, the Varian brothers, here they are, it's Sigrid and Russell. These boys were working out in Palo Alto. That's where Varian still exists, and some of you work for Varian. Unfortunately, you guys don't make the vacuum tubes anymore. Yeah, I think you still make vacuum systems, right? You do vacuum systems, and then you make accelerators with CPI vacuum tubes that the Varian brothers helped to invent. And they did this in 1939, and kalizo is a Greek word for wave. And that's because it describes very interesting how a klystron works, and I'll describe that next. Around the same time as when they were discovering, the British discovered the magnetron, which is a oscillator that can produce lots of RF power, and it was eventually perfected in the United States. The Nazis had started to invade Western Europe by this same time frame, and radar was developed. Actually, it was developed prior to World War II, but it was greatly improved during World War II, and the invention of the klystron and the magnetron were responsible for saving as many lives as and ending the war quickly as the atomic bomb. Okay, so here's a little cartoon of what a magnetron looks like, a klystron looks like. First of all, you need to have a cathode at one end that you heat up with a filament current. Depending on how much power you want your klystron to put out, depends on how much and how hot the filament is. The cathode material on the filament can be oxides of some very exotic materials that, when heated, literally let the electrons jump off very freely. So it's a good source of electrons. And this is just schematically showing electrons jumping off. It typically has a series of cavities. I'm showing 4 cavities here. Some have 3, some have 5. It's all a function of what the bandwidth of the klystron is supposed to be, and of course power levels. There's an input on it. It's coupled, typically a loop coupling on the input, so that you can get energy into the very first cavity. And there's an output coupler on the outside, so you can extract that energy. And what happens next is this thing starts to bunch the electron beam as it starts going through the device. This is called velocity modulation. So the first cavity puts electric fields in there that takes this continuous ribbon of electrons, and some, depends on where they are on the RF wave, some go a little bit faster. Nothing's relativistic in here. These guns are anywhere from tens of kilovolts to a couple of 100,000 kilovolts. And it starts to velocity modulate them, and some go a little faster, some miss the phase, some go a little slower. And what happens now is they're starting to get bunched. How tightly they get bunched starts to change the spectral characteristics of the image current that's going through the cavities. So just as you saw when you're doing your beam signals, as you saw that as you changed into sharper looking pulses, you started generating lots of Fourier components, okay? And in this case here, you're starting to bunch them at the RF cavity frequency. And so at the RF cavity frequency now, you're now putting little pings into a cavity that wants to hear that exact ping. You know, almost as though you had a nice crystal wine glass, you know, and if you ping it, you'll hear a certain tone. And then of course, if you were to sing it at it, you could actually break it, because you'd be pouring energy, or your loudspeaker. They used to have a commercial with Memorex where they had an opera singer shattering glasses, showing how good their tape was for recording things. But if you know what the resonant frequency of anything is, and you bombard it with that frequency of energy, it starts to collect it, because it's a resonator. It's got a certain cue. But at some point, every resonator gets to where you cannot put much more stored energy in it before you shatter it. Okay? So here, the beam is going by, and it's going ping, 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 and if it's designed very well, and getting bunched a bunch more, by the time it gets to the output cavity over here, it's got a nice tight bunching, and it's now putting a huge amount of energy into that final cavity. So you have to adjust this output coupler to take that energy out. And all along, of course, this took just a little bit of power to do it, but the beam itself, if you have a, say you had a 10 kilowatt klystron, well, then you'd probably have a 20 kilowatt electron beam. And if you design it well enough, you can get a klystron to be 50% efficient, which means by the time it gets over here, it's going to take half the energy of the electron beam out. The rest of it crashes right into the collector and starts heating water. So now when you run a klystron, you want to run it as efficient as possible, but unfortunately, if you run it to where it's giving you that maximum efficiency of 50% out, as we already talked about a little bit in amplifiers, it does go into compression and start to generate nonlinear characteristics. And can you tolerate that? That depends on your system. Will your cavity filter out all this other stuff? That's fine. Where does all that reflected energy go? If I don't have a circulator, it goes right back to the amplifier. Can the amplifier take a reflected power over here more than the spent electron beam? Hopefully it can, because a klystron, when there's no RF applied to it, is 0% efficient. The beam keeps on crashing right into the collector regardless. So that's not what's going to kill it. What's going to kill it is someplace over here. This thing is under ultra-high vacuum, maybe 10 to the minus 9 or better torque. So the outside world over here, if I'm going into a waveguide or a coax, I don't want to have that under vacuum, because having a huge vacuum system, anyone who here's dealt with an accelerator, the vacuum system that goes around for miles in the Tevatron or 17 miles in the LHC is an immaculate environment that you'd like to have. Not only people take their shoes and socks off before entering, you just don't welcome into your house at all. It's a sealed system. So, but you have a window here, which is typically some kind of a ceramic window, dielectric ceramic window, because the dielectric ceramic window will allow the electromagnetic waves to propagate right through it and get into your coax. Problem is reflected waves. We now know all about reflected waves. What happens when you get a reflected wave is you get a voltage standing wave ratio. And so now, if all of a sudden your cavity is taking only a certain section of it, but you've generated harmonic content, those reflected waves come right back to the window, and if that window happens to be at a standing wave peak as opposed to a node, the voltage is going to go up. And if the voltage goes up, is it going to break down and have a crack across that ceramic window on the klystron? If that's the case, the vacuum here breaks, you no longer have a klystron. If it's like the klystron, we have a Fermilab that's over $250,000 that just went kaput, and of course it takes a long time to fix, so you always have to have hot spares. So that's why you want to worry about that, and that's why many times you'll end up putting a circulator there, or you end up putting a very fixed number of integer half wavelengths between your window and your cavity. Because what happens on a half wavelength, if there's a node here, then a half wavelength later, it's a node there, okay? If this was a quarter wavelength and there was a node here, quarter wavelength, it's a high voltage point. That's bad. So at Fermilab, we don't have circulators on our outputs, but we do running at only one frequency, and of course, the amplifiers can take the reflected power, but you don't want that high voltage to happen at that window to save the ceramic break on the tube. Okay. But that's not all, of course. It takes a lot more in order to make all of this happen. You need a modulator, if it's a pulse system, to provide the voltage to get the electron beam going. In the case of our 12 megawatt klystron, that's about 180,000 volts, and it pulses on for on the order of 3 to 400 microseconds. The beam is actually good for only about 120 microseconds. The rest of the time is filling up the cavity, okay, and then waiting a little while it filled up the cavity for the feedback system to make it nice and level gradient, and then the beam comes along, and then you let the energy come out. The electron beam is not going to go straight on its own. It needs solenoidal focusing, so every single one of those cavities has got a solenoid around it, and those things can chew up an enormous amount of juice because they're electromagnets, but that allows you to tune the lattice to make it functional. You've got a filament voltage over here, which is substantial. I think I said the other day in our LINAC at 201 megahertz, a 5 megawatt triode is the output stage, and its filament runs at like 3 or 6 volts and 7,000 amperes. So that's a serious beast. And then, of course, the collector, no matter what, has got to be able to take the full energy of the tube. So if you had a 10 kilowatt tube and a 20 kilowatt electron beam, that collector's got to be able to dissipate 20 kilowatts. And that's an essential. And then, of course, you got to interlock the whole thing. It's a pretty complicated system, and you got to monitor the body current too, because electrons sometimes will escape the confinement field of the focusing electrons. And of course, if it starts hitting the body, and each time you start charging up a piece of metal, it could come up to a high voltage that could hurt you, or you'll just start measuring the ground current, and you know it's time to turn the thing off because a power supply could have failed, a power supply could have had ripple on it. Something is forcing this beam to get out of the vacuum envelope. And if you continue to run that direction, you know, now we're talking about klystrons that can have megawatts of power. You keep running that direction, at some point this electron beam will drill a hole in something, and then it's all gone. It may not even be rebuildable. What typically will go nasty on a klystron is the cathode will eventually become depleted. But these Clystrons we've installed in the 1990s in our 805 megahertz, that's an 805 megahertz cavity prototype from the LINAC, they can last well over 100,000 hours. There's still, I think, at least one that's original from 1993. Okay, it's amazing. So, everyone talks about longevity of solid state. A well-designed tube lasts a long time too. That's over 20 years out of one tube. Okay, now what they've done, because people want more and more power coming out of a klystron, is they go to something called a multi-beam klystron. And I know what they're doing at ESS for Dave is they're using the same technique for an IoT, which we could talk about at a later time if you're interested. Like I said, it's not really a power RF course. But the importance about going to a multi-beam is to reduce the space charge. At some point, you can only put so many electrons together before, and these are relatively low energy, so they're not relativistic. So the space charge forces really want to blow the beam apart. Tough to keep it focused. It's tough to keep it focused. That means it's tough to stop losses. It's tough to get the beam bunched as tightly as you'd like so that it can clean the output cavities to get the power. So you go to multiple beam, and now they've currently been able to do this on Clystrons that they were planning for the ILC, and they come up with 10 megawatt Clystrons with 6 beams in it. And now instead of having, it's all still conservation of power, you can have a lower kinetic energy beam, but you've got 6 of them at a lower current, lower space charge, so you can actually get a lot of power in a physically smaller tube and keep the efficiency up. And this took quite a long time to develop multi-beam Clystrons, but they are routine these days. Some typical things with a Klystron is 40 to 60 dB a gain, kilowatts to tens of megawatts. They could be continuous or pulsed. They can be hundreds of megahertzes. We just bought as a potential to replace this triode I told you about that generates 5 million watts. There is no longer any device other than the one we use to do that. We are almost the sole company in the world, and this company is now starting to charge us $300,000 a piece. And they know we're the only company. And the problem with that tube is it barely lasts a year, 9,000 hours. So our maintenance and running cost is a big deal on those LINAC tubes. And the LINAC is almost 50 years old, and getting replacement parts for everything else is going to be a headache. So we are pursuing this superconducting replacement that, if it were successful, won't really be ready for almost 10 years, which says the existing LINAC has to run at least 10 years. And what we did as a plan B is we just went and bought a 5 megawatt, 200 megahertz Klystron. Now this thing is long. It's probably about 19 to 20 feet long, so we have to make it to where it lays on its side because the roof is not tall enough to let it stand up. And of course that cathode, which I didn't get into, the cathode must be submersed in an oil bath, and there's a transformer in there, just because if you're up at 180,000 volts, on a humid day, it's not going to hold off the voltage so much. So now you've got an oil tank which has got a big hole in the side to let the cathode come through. You don't want it leaking all over the floor. Horizontal Klystrons are a little bit more of a headache. And the best ones are 50%. They can put, there's something called, and those of you who know about TWTs, you can put, and even IoTs, you can put something called a depressed collector. So instead of having one power supply in the collector, you can have 2 or even 3. And what it does is before the electrons hit the collector plate, there's a power supply within the collector supply that decelerates the electron beam, recovering some of that energy, and you can do that in several steps. And then by the time it hits the copper of the collector, it's lost energy because you reclaimed it in the external power supply. But every time you do that, you're adding more complexity to the system, and more complexity means more cost. So in TWTs, the TWTs they put into outer space, many of them have triple depressed collectors, because as you can imagine, there's no power plant in outer space other than your little plutonium reactor that you brought with you, or the sun. These deep space things, the stuff we're sending out of there, those have got plutonium reactors on them that generate maybe a few hundred watts up to a kilowatt. The sun, if you're in near Earth orbit, of course, you've got a kilowatt per square meter, but the conversion efficiency of solar panels is 5–10%. So power is an absolute premium in outer space, even in near space. And so when you put and you put TWTs up there, because they have very broad band, and that means you put lots of information on them, but they're power hogs, And I want to get the most efficiency possible, so they end up putting multiple depressed collectors because it's more expensive, but I'm sending it someplace where I can't send anyone up there to fix it. So that's another trade-off you make in system design. Okay, this shows what a typical klystron characteristic would be. On the left is a power gain curve, on the right is a phase versus gun volts curve, and the red curve right here is what the transfer function looks like of input power versus output power. These are some of the measurements you'll be able to make on these little puny amplifiers. What you'll notice, something silly that happens, is I get to saturation, and it'd be kind of nice if it stayed at saturation, but if I start driving it higher, the power ends up going down along with the gain starts to going down. That means you can easily, if you think you're driving over here, you're going to say, give me more is going to be giving me less. That is not a very stable place to operate. So, and the amount of distortion you're going to be generating over here is potentially intolerable. So you really kind of want to be down over in this neighborhood. So even though you're at a 12 megawatt klystron, we typically run them in the 9 to 10 megawatt regime so that they stay in a semi-linear performance mode. The other thing that happens, which is pretty darn critical, is where this is the gun voltage. So this is the giving you the acceleration to the kinetic energy to the electron beam inside the tube. And what we have here is one's a phase detector, and on the right side over here is showing the error volts, and that's the this is an error volts over here, which is plus and minus a voltage or something like that. But the important thing to notice here is that the actual phase as a function of power changes quite a bit, 30 degrees per volt. Now, is that important? That means if I don't have a very well regulated klystron, and so you have to put money into your modulator, that says depending on how I'm running this thing, I'm going to get a different phase output. But remember the guy surfing on the wave, he's got to be at the correct phase in order to accelerate beam. This is especially true in a proton linac, where the beam is not relativistic until it really gets into the GeV. And so most linacs run up to a GeV or a few GeV, and building a proton linac for those first few hundred MeV is very tricky, and the phase is ultra critical. So you have to have a very well stabilized electron gun in order to make that happen. Here's multi-beam klystrons that were manufactured by 3 different people, and they're at 1.3 gigahertz, because the big push for the last 20 years is the ILC, which was chosen to be 1.3 gigahertz. 1.3 gigahertz was not an accident. About 20, how many years ago? Because I was there for that. Well, between 20 and 30 years ago, I first started working on ILC-related things in 1992. Okay, so that's 23 years ago, right? And the U.S. Department of the Military had contracted Boeing up in Seattle to build a free electron laser. This is when free electron lasers were a pretty new curiosity, and they glommed onto it thinking like, hey, this could become a weapon. And so they spent an enormous amount of money to buy, to build this free electron laser, and they had, let's see, who made those? Who made the klystrons at ASIO? First, I think it was, it could have been Thales, which is hard, that's hard to believe because they're French. Who was it? It could have been L3, which is Lytton, or it could have been CPI. I can't remember now. I have to look it up. But anyway, they had, the program got canceled, of course. Military, if you haven't shown me how to kill somebody in 3 years, it's like time to pull the plug and let's spend money somewhere else. So they had this little army of 23 beautiful klystrons at 1.3 gigahertz. These were 5 megawatt klystrons at the time. And Maury Tigner, which some of you may know, he and I went together out to Boeing to try to charm our Boeing pals into giving us 2 of them. Of course, the government owned them and we were government, so we figured, all right, that's, they're supposed to be able to give us this kind of stuff, and they're here with, you saw the candy shop of all those boxes we had. Can you imagine, 23 klystrons with pulse transformers, solenoids, the whole thing there. We're just there, and we did. We got 2. The first one is still at Fermilab, the other one went to Cornell, which is where Tigner was from. And that became then the center why it's 1.3 gigahertz, because there was a power source that existed from a previous user. And that's almost all the case. I mean, that's what's going on at ESS. They're at 352 and 704 megahertz because CERN pioneered those frequencies. and therefore they wanted to stick with something that someone had already done. Of course, they still need to develop lots of different kinds of power sources, but many of the frequencies that exist because someone had already did the NRE cost to develop the RF power source. And so that's where you see a lot of these frequencies routinely show up. Okay, well, I'm going to talk about the IoT. Now, an IoT is another interesting beast, in that it looks a little bit like a klystron. And it has a cathode on it, and it has a gridded cavity on the first part, solenoidal focusing cell, and a cavity on the output. IoT stands for inductive output tube. They have been around they were invented certainly in the middle part of the 20th century, but they really came into prominence in the 1980s is because you can build one of these things where this cavity and this cavity could be externally tuned. So these things work great at UHF frequencies, and until maybe just even a few years ago, every television station essentially in the world in the UHF regime operates between 400 and 800 megahertz. And an IoT is a very nice device to be able to give you 10, 20, 50 kilowatts in a box, better than a klystron because it has this grid in there. Okay, so when you don't want to be turning on, you don't bias the grid to be on, as opposed to a klystron, which becomes 0% efficient when you're not transmitting. You can use this grid here in order to control the electron beam. It's like a valve, a gate, to keep the thing going on and off. You still need the focusing coil. You still need the filament. If you want it to be clean, and remember, I think what some of you guys were looking at to see if you saw any 60 hertz sidebands on any of the signal generators, and that's because if your power supply on your signal source is crappy and it's plugged into the mains, and you don't filter the 50 or 60 hertz out, that's going to come in there and put modulation. Well, the same thing will happen here, is if that filament supply has got, power supply filtering issues, it's going to sit there and modulate the electron beam jumping off the cathode, and that modulation is going to carry through on all the cavities because the modulation is so close to the carrier that the Q of those cavities is not high enough to filter it out. So cleanliness in your power supplies is absolutely essential. And otherwise it looks very much like a klystron, and you couple energy out of the output. Some of the details on these things, not so high gain, 20 to 25 dB a gain. And that could be enough, but that says if I need a megawatt, I need 10 kilowatts to drive this. And that's not a trivial thing. Whereas if I need a megawatt of a klystron, I could have 60 dB a gain. I only need 1 watt to drive it. But this device is more efficient, 65%, and of course I can turn it off. You never want to turn a klystron off because it has thermal characteristics. So even when we're not running beam, we got that thing firing all the time. If we're going to be off for a long period of time, you'll turn the filament from red heat, which is what we really call it, down to black heat. So you turn the juice down just enough to where the thing's not glowing red hot, because they are really glowing red hot, and it doesn't boil off as many electrons. But you don't want this thing to go from hot to cold, because that thermal cycling is going to potentially break the tube. So they're always on. But you can turn it on and off, and it has a higher efficiency. Bandwidth is on the order of 1%, very similar to what a klystron can do. And they have long lifetimes, maybe not as long as a klystron, but they're also a little bit cheaper than a klystron and more efficient. And here's some IoT characteristics that we did. We bought, must be 3 or 4 years ago, for Project X, now PIP2, is one of the main parts of the project is 650 megahertz. And we need, well, for the full project, we need like 256 30 to 60 kilowatt sources for PIP2/Project X at 650 megahertz. 650 megahertz is half of 1.3 gigahertz, and everything else is sub or harmonically related or higher harmonically related. And like I said, that's not an accident, it's all picked because of something that exists. And what this shows here is the power conversion efficiency. And again, as all tube-type amplifiers do this, if you're running at very low power, efficiency is low. But as you get close to saturation, you can start to approach 50-60%, which is very nice. But unfortunately, the gain is not so great, so you need a pretty beefy drive amplifier. And drive amplifiers are not cheap per watt either. So that's something that has to be taken into account if this is the way you want to go. Okay, here's these IoTs that we bought from this company in Boston, actually a television station in Boston. That was right at the time where the whole country was switching from analog television to digital television. And the difference between analog television and digital television is analog television, in order to get the full dynamic range of the picture, you used to have this peak to sync dynamic range issue. In other words, you had a very wide dynamic range, so your amplifier had to be able to amplify with no distortion this high dynamic range signal. And it depends on if there was black on the screen or white on the screen or what color it was, you had to have this large dynamic range. So that makes for broadcast television was pretty inefficient, and of course you had a limited bandwidth. Along comes digital television, which came along way long ago, but when you start thinking is like, we're going to make the decision, and everybody in the United States is going to have to buy a new television. Or if you remember when it first happened, it says, here, for $40 the government's going to give you this box to make this incredible new bright signal that you can't believe you're like you're watching a movie, and it dummied it down to the old kind of watching television. You'll never even see those I'll bet nobody even has one of those dummy boxes anymore.
I have one.
You use it?
Not anymore.
Yeah, I didn't think so. Yeah. So you have one, but you don't use it. But it was a big deal because you had to force the whole country to buy new hardware. Now this made the hardware people fabulous. But the beautiful thing about the digital thing now is it no longer needed this high peak to sync ratio dynamic range, because the digital signal it's spitting out has got a very limited dynamic range, and it's putting out the same amount of power all the time. So now all the people who own a television station saying like, well, this analog signal is it's costing me my power bill. Remember, most TV stations are on 24/7, and it's costing them a lot of money in electricity. So let's bite the bullet. And it was a forced bite the bullet, unless you were some small maybe Czechoslovakian station out in Utah or something like that. They didn't force certain things to go to digital television if they were at a certain low power level. But almost everybody else saying, look, on this date, it's going to happen. And so there's a big rush to go out and buy new, more efficient, less costly amplifiers to operate. So at that time there, after I bought these three, they said, hey, we got a sucker on the line. I got more phone calls saying, you want to buy our TV? and I said, no, we have three now. Thank you. And we've had them running. And the thing is, they're tunable, so we could tune them to 650 megahertz. And we have three IoT stations running at Fermilab that'll spit out 30 kilowatts. And I've had them running for 3 years. Unfortunately, I have no cavities to test yet. So it was just an option of opportunity.
Was that an MDB?
Huh?
Is that an MDB?
Yeah, those are out of NDB, right. Okay, then there's solid state topology, and we do have two 75 kilowatt amplifiers we just purchased. They arrived this past summer. But when you want to make a lot of watts, it takes a lot of transistors. The units we have got 16 drawers, each loaded with 8 transistors, so 128 transistors, each running at 600 and something watts, all combined to make 75 kilowatts. This thing, I'll have to show a picture. This thing is 3 relay racks, but not just standard relay racks. So it's about 4 meters wide, 3 meters tall, and 1 meter deep. And it has power supplies and lots of stuff in it. It's pretty complicated. It's taken us months to get it to behave properly because it was a new product from the company that we bought it from. And solid state's coming along, but solid state, if we're working in the microwave regime, right now at LCLS2, which is going to be the light source they're building at SLAC, in the old SLAC tunnel, they're going to use solid state CW amplifiers at 1.3 gigahertz. And at 1.3 gigahertz, those will end up costing probably $15 to $20 a watt, so it's a very expensive thing to do. A colleague of mine and myself at Fermilab, we just patented a running a magnetron in the injection lock mode, and that is a $2 to $3 a watt solution, which we have already proven running a superconducting cavity at 2.45, and we're looking to do the next system at 1.3 gigahertz if someone will give us some money. So we're still waiting for that. Okay, solid state certainly can have gains on the order of the same thing as the Klystron. 100 kilowatts is it's getting to be a pretty damn big, but their amplifiers will do that. Once, but 1.3 gigahertz is at the edge. As you go to higher frequencies with solid state, the devices must physically become smaller. And why is that? It's because the junctions have capacitance to them, and yet you want to carry a lot of current. So if you want to carry a lot of current, you need some junction. And at some point, if you make the junction so large to carry the current, the capacitance are such that you can't make a matching network to get them to work at the frequency you want. So at frequencies above a gigahertz, the transistors physically must get smaller. I can't get 600 or a kilowatt out of them. Maybe I can only get a couple hundred watts. As I go up to 10 gigahertz, they start getting really puny. And now the amount of dollars per watt, if I want lots of watt, it goes up in a nonlinear fashion. So solid state is still a pretty good option for below a gigahertz. Above a gigahertz, it's got a ways to go before it's price competitive. And of course, they operate at low voltage, typically 50 volts as opposed to the tens of or hundreds of kilovolts that would exist with a tube.
Can we just continue to parallelize them?
Sure, and that's exactly what's going on in the solid thing. There's more and more things in parallel. More and more things to break. More and more things depending on how am I combine. Like the amplifier we just bought, they built in a protection system that if, so there's 8 transistors in each slice, and if one transistor goes, it allows the amplifier to continue running. But now it's put a mismatch in the combiner tree. And so they said, even though this amplifier is made to do 75,000 watts, as soon as one of those transistors blows, you can't do more than 50,000 watts. So you can run, is 50,000 watts enough? If it isn't, you got to fix it. If you have to fix it, you're down. Your beam's not running. You're going to get charged for that. Okay, and guys at Fermilab know very well. They have a downtime log, and they see who all the bad guys are. And the bad guys really at Fermilab are the water guys. Always. Always. It's not their fault. This water's just a pain in the ass. And someday, if you work in a real laboratory, you will see that in spades. Okay, here's a typical peak at a solid-state amplifier. You've got, and these are typically two MOSFETs in parallel. Could be done with gallium nitride. There's silicon carbide is the newest thing for lower frequencies. And these little thingies here that you're seeing, those are actually hybrid transmission lines by using coax cables. And this whole thing is, maybe 2 inches by 3 inches, something like that. And you've got hundreds of them built into a pallet. This is actually what one of our amplifiers looks like. We bought this thing, a 10 kilowatt thing, at 325 megahertz, stands about this tall, and we use this for testing couplers at 325 megahertz. Okay, let's get into now, so now we've gone through all the amplifiers and some of the basics. We're very close to done. How do I get my energy from the amplifier to the cavity, or your kicker, or whatever it happens to be? I have to use a transmission line. We've already talked about transmission lines. There's lots of different kinds of transmission lines. There's waveguide and there's coax. We saw strip line and microstrip. Well, here, if we're doing 1.3 gigahertz, which is a popular number, here's the waveguide for that, which is WR650, and it's like 6.5 inches by 3.5 inches. And, that's a pretty good chunk of cross-section that you have to make room for in your gallery. Now, the thing is, you can also use a 3-inch coax at that point, and it has an insertion loss of about 0.7 dB per 100 feet, and it can only do 640 kilowatts, but the waveguide has a quarter of a dB per 100 feet and could do 13 megawatts. Okay, so now you've got a decision to make. That 3-inch coax occupies half the volume of the waveguide, but I have to pay for those lost watts. Am I going a short distance? Am I going a long distance? Many times you'll see in an installation that you'd like to have the amplifiers upstairs if at all possible, because they are going to break. And it would be nice to fix them up in the gallery by having maybe something you just roll right in, or you fix it in place. Or you have something down in the tunnel where you don't have to worry so much about transmission line losses. This is a decision that you have to make. If the power level is not high, certainly coax is much easier to work with than waveguide, and that you don't have to put hundreds of bolts every few feet in it. But it's a question you need to worry about. Also, coax is a TM, and is very broadband. So for all our stochastic cooling stuff, we were trying to put 1 octave of signal in. Waveguide wasn't an option because when you take a look at the characters of the waveguide, it's very dispersive. Again, not all frequencies travel at the same velocity, so I don't have a linear transfer function with them. Okay, so now we're starting to put the whole thing together. We know about the cavity, we know about the power sources, we know about matching, we know pretty much everything we want to know about trying to make a system. And so now we just put it in some schematic function, to where I've got a generator that generates my power, but we know it's not the right impedance, so I need some kind of a matching network to go into the equivalent model of the cavity. And the cavity has an R and a C and an L, but it also has the beam and a generator. And the beam has an impedance. And all of this business is sitting, looking at this very simplified circuit model, and this, you know, people still consider this a nice way of doing things. Okay, well, here's the business, as everyone understands, maybe they understand radar, is it works due to poor matching. And in the case of flying on a commercial airline, that's great. It's good that it's made out of metal. And now I'm starting to think, okay, if I'm flying on a 787 or something that's made out of carbon fiber, I hope they put a lot of foil in that thing someplace just to reflect the microwaves coming from the radar. Certainly the engines have got a lot of metal in them, but if you end up making things to where it's too stealthy, it's tough for the radar to see what's going on. So that's good. This is one case where poor matching is good. All right. Another case is that guy. You don't want to see me coming when I'm trying to kill you. And so it's covered with all kinds of absorbos and reflective surfaces that misguide the microwaves, and it makes it harder to detect. Okay, so in that case, it's very good. And now I'm starting to wonder if those 787s or something are looking a little bit like a B-2. I'm gonna ask that question. I'm gonna find that out.
I think the fuselage is still aluminum.
You think so? Just the wings are carbon fiber? Okay, good to know. I want that verified by next Thursday. Okay. All right, so now how do we do matching in microwave language? All right, well, in order to be able to match something, you have to be able to see which way the waves are going, this way and that way. That's what directional couplers do. Some of you already measured directional couplers. All of you will eventually measure directional couplers. And what they do is they just take a very light sample of the waves going this way and that way. And when you see a bunch of energy going this way and almost none of that energy coming back at you, then you know you're matched. And that's what you've been doing when you're measuring things with the network analyzer and the like. So that's one of the tools that helps you to measure it. But to actually do the tuning is you can have something like this, which is a 3-stub tuner. Well, you guys are going to design a 1-stub tuner using coax. Okay, you can do the same things in waveguide. And if the reason why you go to a 3-stub tuner is a 3-stub tuner gives me more parameter space to match almost any impedance into the 50 ohm, or in this case, whatever the waveguide impedance happens to be. So triple stub tuners can match almost any impedance discontinuity to your characteristic impedance. And that's a part of another course where you can show how that's the case. Okay, the more stubs you have, the more finessing you have. But this, you can just buy this at the store. This is an isolator circulator, which you need in case you have something that's so mismatched and you have no choice. It gives you the isolation so that your power source doesn't get hurt under any condition. And then, of course, you need someplace really for the energy to go should it not go into your cavity, so you have some kind of a load. All right, so now let's go ahead, and we're taking that circuit I had earlier and just simplifying it by just doing transformer ratios and the like. And so now you see you still have the cavity, but now you have 3 impedances in parallel. And you have 2 generators, because the beam is an ideal current source. It literally, no matter what hole I put it through, it's going to go through. Now, it'll certainly go through once, without a doubt. It's going to leave some kind of a wake field behind it, which could grow and be absolutely ugly to where the next time I come through it, bad things can ensue. Right? But it's going to go through once, and that's really the definition of a current source. I don't care what impedance you got, I'm going. And so it's a current source. And we look at the power generator also as a joint. Well, this is the thing that you end up having to match. And if we're just simply putting it like this, is you got an impedance versus frequency. And this is what you guys have been doing when you've been trying to match, those of you who've gotten that far, is you're trying to make the amount of return loss coming to your source minimize at that frequency. And for a cavity, typically, it is a single frequency, so you can match it really good even with just a single stub, which is nice. Okay, so now we're going to put the whole thing together. What have we got to ask? What's the duty cycle? All right? Is this a CW machine? Is it a pulsed machine? Because that's going to be a function of how much energy is involved in building a system. Okay? What's the most gradient I can get? This is the big question. Back in the early 90s when they were figuring out, should we make the ILC out of copper or should we make the ILC superconducting? Okay, and there were pros and cons for both. Eventually superconducting won because of some very specific issues with the duty cycle involved and the gradient. And you have to wear, cryogenics is really expensive, and building cryo modules is expensive-er. It's really a big deal. But I need to know what that is, because at some point before anyone designs, there's a reference design report for any accelerator that's being designed. And you know if you want to accelerate so much beam or so much beam power that you're going to have so much shunt impedance and so much power to make the voltage to make that happen, but not so much shunt impedance to where the current is going to cause instabilities that the beam won't go through. And this is all what the physics design of the accelerator's got to be, and these are the parameters that you're given, and then you got to start asking these questions. Okay? Well, is there a power source available? Again, we don't just choose one at random. Now I want to build a magnetron system for 1.3 gigahertz because we own 1.3 gigahertz cavity, and I could do a complete proof of principle with a full cavity and the magnetron. And so I want a source. There's no magnetrons at 1.3 gigahertz. They can make them, but there's nothing on the shelf. So now that says I got to ask CPI or L3 or E2V to say I need a 1.3 gigahertz, 100 kilowatt, 10% duty cycle magnetron. They say, no problem, give us $1 million. Okay, how many do you want? Just one or two for starts, but eventually I want hundreds. And so that's what, of course, makes them interesting. But they're going to charge you $1 million for the first one, which you have to cough up. So a lot of the projects say, well, let's skip that step and we'll pick a frequency where the power source and the NRE exists. Now that's for a little bitty magnetron. A multi-beam klystron is tens of millions to develop because they may not guarantee that it's going to work. Best effort, and then you still have no power source. Does that fit into your building schedule? I don't know. Talk to your boss. Okay, then, so now, can I just choose a frequency indiscriminately? Well, not necessarily. Here's a 53 megahertz cavity that we use in the anti-proton source. Why 53 megahertz? Because the machines that fed it, that have been around for 30 years at the time, operated at 53 megahertz, and you wanted to do a synchronous transfer from one machine to the next. Okay, and the 53 megahertz power sources kind of existed. They used triodes and tetrodes, which down at 53 megahertz, certainly for when Fermilab was designed, was the way of doing things. There was certainly no solid state to help you there, and it's way too low in frequency in order to have, klystrons or magnetrons. And 53 megahertz is kind of a nice number because we did want to have a lot of bunches, and the machine was going to go around for 4 miles, and at 53 megahertz I could put 1,113 bunches in the machine. So, you do a little trade-off there, but the cavity is like a meter in diameter and like 2 meters long. This is a folded transmission line cavity, just like the one Dave was showing you in the cavity lecture. So, I don't know, is that acceptable? Depends. Okay, how about X-band? This is what the NLC was working on back in the early 1990s. X-band was 11.4 gigahertz. You can see this thing is 6 centimeters. The hole for the beam is right there. And then these little cavities on the outside with little slits coupled to them, those are higher order mode dampers, is because when you have this beam, that's about less than the size of a pencil. And of course this thing was going to be almost 30 kilometers long. So the beam going through that leaves a significant weight field, and the beam bunches, it's electrons in this case, the beam bunches are very, very short, so there's an enormous number of higher order frequency modes that could be left. And when you have a structure that's about a meter long, these things are centimeter or so thick, so you got like 100 of these little cavities in each one, all brazed together, nasty things can happen, and those higher order mode things were able to absorb that. Made out of copper, and 11.4 gigahertz. The unfortunate thing is this thing didn't need kilowatts, it didn't need megawatts, it needed hundreds of megawatts in order to get the power to get the this was like 100 and something MeV per meter, maybe 3 or 4 times more than even a superconducting cavity can do. But you had to be able to combine 8 multi-beam or single beam klystrons in order to get the 400 to 500 megawatt pulse to make this do it. That was and the way they wanted to do it was a complete nightmare, and it was a really showstopper. I vetoed that one. And then of course there's the famous superconducting 1.3 gigahertz stuff, which is prevalent throughout the world these days. And it has a nice big hole, 70 millimeter ivers to go through, 9 cells, 1.3 gigahertz. Part of power source is there, so a number of things. The DAISY FEL is working at 1.3 gigahertz. Fermilab stuff is at 1.3 gigahertz. but the Europeans are doing 704 because they had 704 megahertz in their past. So there's two main camps on the planet, and superconducting seems to be the way of the future. And we won't get into the politics of that, but that's what's being pursued in lots of places. All right, so superconducting, 10 to the 9th Q unloaded, 10 to the 7th possible. When you pulse the fields, they exert mechanical detuning forces, which are called microphonics. So if you've ever been around in a laboratory where you've got kickers pulsing or power supplies ramping, whatever it is when you have huge magnetic fields someplace, they vroom, or they make dink, dink, come down to your pulse transformer. Same thing happens to the metal inside the superconducting cavity, is you're ramping up and putting huge magnetic field forces in the cavity, and it's mechanically changing the cavity. Now, everything feels Lorentz forces. It's just that when you have a Q of 10 to the 7th plus, that what happens, and I think I can play that again, I'm not sure if I can really go back one way. You know, is it sit there and it does that, not curse, not on this, this is Lorentz by the way, and it sits there and moves a microscopic amount, but that microscopic amount, as I show on the graph on the right, can be many bandwidths away. Now, you're going to find out, as you start measuring the cavities here, is if I don't put energy in at the frequency it's resonant, no energy is going in. It's all bouncing back toward the source. So if I can't fill the cavity, I can't get the cavity to accelerate. It's the old, you know how to take the reservation, you don't know how to keep the reservation, for those who watch Seinfeld. You guys are all too young to watch Seinfeld too, it looks like. So, and in the case of some of the cavities, like the ones we're working on for PIF2, have cavity bandwidths of 10 to 100 hertz wide, and we're up, in our case, we'll be up at 650 or 1.3 gigahertz. And so the ability to move full bandwidths away says, if I can't figure out how to track that cavity, I can't even fill the cavity up, which means I can never accelerate beam. And that's an issue. So in pulse mode, Lorentz force detuning is nasty. Well, there's a way you can combat that, and we actually are doing it. Most people are doing it. It's not been ever done in an actual operating accelerator yet. And for that matter, SNS, which is a superconducting linac, had piezoelectric tuners in them, but their Q was substantially wider. They were on the order of kilohertz because they have such a high beam current. Is they decided to take the tuners out because it's a piezoelectric material and it can crack, and once it cranks, it no longer acts as a mechanical. Piezoelectric devices, something if you apply an electric field to it, it mechanically changes, and vice versa, in case you guys didn't know what that was. A piezoelectric device, you know, and there's lots of ceramical devices like, well, the thing that's inside here, okay, that ruby crystal that's inside the BMW is a piezoelectric device, which is the reason why I can excite a wave on it acoustically, because it physically moves when I apply an electric field to it. So these are an interesting beast that can happen. And here's a test that was done at Daisy years ago by Lutz Luge, who was worrying about compensation for force detuning. And what we see on the left-hand scale here is in red is without using piezo tuning, and what we over here is detuning in hertz versus the time of the pulse. And you can see here we have a pulse that's 1.3 microseconds, actually 1.3 milliseconds, excuse me. And without it, this thing, for the entire time that the gradient is filling the cavity, it's detuning. It's not at the right frequency. With the piezo compensation turned on here at 600, you can see that they were able to get the detuning to be less than 50 hertz. Now, if less than 50 hertz is okay, because maybe you have a couple of hundred hertz, case closed and the low level RF can maybe help fix your phase. If the case is you have a 20, 30 kilohertz wide bandpass, that's not good enough. So you have to come up with a better tuning mechanism. And here's again what you can come to expect then. Remember, as this thing is detuning without any feedback, is the frequency is changing. So even if I'm putting in energy at a very fixed frequency, the frequency is changing. So I'm getting down to the slopes of the pass band, and what ends up happening is I'm filling it up. But this is the gradient here now in megavolts per meter. It's not flat without any piezo tuning, and it rolls off. Well, this little bit here is flat, so the beam that comes out at that time is going to have some energy, but the beam that comes over here is going to have a totally different energy. If I have a huge energy spread in the beam, and that continues as I go down your linac, at some point you don't have a very monoenergetic beam, and that's definitely going to cause people to complain, or you'll lose beam, or anytime you want to kick it someplace, you're going to spray it instead of get a nice kick if you're going into a circular accelerator. So you want to keep the beam monochromatic if possible. And of course here the phase is doing the exact same thing with the piezoelectric. It's keeping the phase within 10 degrees or so. And these are all proven studies that have been done. Okay, other sources of microphonic noise. And this is really true. You got vacuum pumps someplace. Now when we did this test with the magnetron back at Fermilab several months ago, and the test stand that Elvin had let us do the test, it had this beautiful vertical doer, and it had 3 Ritz blowers 10 feet away, and you know, to allow us to bring the 4-point Kelvin doer down to 2 degrees Kelvin. You have to pump on it. That's the way you get liquids to get colder of any kind, is you just lower what the vapor pressure is, and it plummets down. And why do you want to be at 2 Kelvin? That's 1.8 Kelvin. That's the lambda point of helium, at which point it becomes a superfluid. Superfluid gives it infinite conductivity. It's not boiling. Boiling is microphonic noise. That's a bad thing. So you want to operate there. But in our case, and oh, by the way, while you're pumping on this, you're sucking helium out of there at incredible rates. So the doer doesn't stay filled for more than an hour. And of course, our test was filling the doer up with 500-liter cans. So we tried that for a while, but the damn pumps were 10 feet away. And for instance, at the LHC, where they do run at 2 Kelvin, is the pumps are on the surface, the machine's down 300 to 500 feet underground. So it isolates that. Okay, so microphonics can come from mechanical nasties that are laying around. You know, old Curly over here, plumbing. I'm not sure about your laboratory, but we have noisy plumbing. If there's any air whatsoever inside the plumbing, or what do you want to do with plumbing? You want turbulent flow. That's the way. If you get laminar flow inside your cooling systems, you're not going to be taking heat away from whatever's getting hot on you. So you need turbulent flow. What's turbulent flow? Noise. And if that noise happens to be near that cavity, it's going to shake the cavity. And when it shakes the cavity, it's going to put all kinds of sidebands on there. And those modes may be absolutely horrible to the beam. And you got to get rid of it. So that's terrible. We have a problem in the Tevatron, which is not superconducting RF, but superconducting machine. And we noticed that every time a heavy truck went by the CDF detector, is all of a sudden, the beam detector was seeing bad things happen. So all of a sudden, and they finally did a test where they closed the roads off to everyone but the fire trucks. And the fire trucks started going right near the CDF, and sure enough, you know, it was the shaking of the trucks going by that caused the shaking of the final focus quads, and the shaking of the final focus quads made the beam miss each other anytime that happened. So that's a bad thing. And then heaven forbid, earthquakes. Earthquakes even, well, I don't know about here in Virginia, they happen even in Illinois, but building accelerators in California has got to be an incredible extra bitch, because it can really do bad things. And where was the place, Dave, that there was the earthquake, and was that, did SNS have an earthquake that shifted the floor, or where was that? Was it what?
J-Lab.
It was J-Lab. It is here. See that? That's right. It wasn't an earthquake. It wasn't an earthquake. I did it.
Japanese lab.
Huh? Oh, J Park. Yeah.
Well, they had an earthquake and it went.
And then you know, the tunnel shifted by 6 feet. You know for sure that the beam's not going to make that jog. So that's a problem. So these are all things that you have to worry about when you decide to go this route. There's other clever things you can do, and we've got some very clever feedback guys. Feedback, remember that, is that here's a situation where you have your signal generator, and then you drive your cavity, which is here. This one says a 13-cell cavity, and you take a little bit of signal back, okay, through some kind of directional coupler. You mix the signal with mixers, all the parts that we're teaching here, right? You take that error signal now, and you go into this sneaky little black box with FGTAs or PGAs and everything else. And what it does is provides negative feedback. So the red right here is an uncompensated, because I can use this piezoelectric device to anti-damp any of this microphonic noise. And here we see 15 hertz, which is a subharmonic of the line, and that could be just something because the pump is turning, and it has several modes that are line related. I don't know where 27 hertz came from. 45 hertz is yet another thing as a function of 60. But you can see, and this is in dB over here, it's actually in dB kilohertzes. This shows what the perturbed nasties are, and with some very clever feedback, is we can do some significant suppression, 10, 15, 20 dB of these nasty microphonic things. As you're starting to see, this has become an extremely complicated system with many things that have to work for it to work at all. Okay, so we now know we got a generator, we have some kind of a coupler that lets us know what's going to the cavity which has got the beam, and we're gonna monitor forward and reverse power. And if I were to take a look at what these probes are here are telling me, is it takes a certain amount of time to fill the cavity. If it's a superconducting cavity, it could be on the order of millisecond. Depends on what the Q is. And then, of course, because the cavity is not filled yet, and therefore matched to the source, is the reflected power, it's all coming back. Because remember in that thing where you had the resistance of the cavity and the resistance of the beam in parallel? Well, the beam's not there yet. Therefore, it's not matched, okay? Because you're waiting for the impedance of the beam to show up. But at some point, you do get to a flat gradient, which you want to start to regulate on. But if you do absolutely nothing, then the beam comes along. Now the beam is coming out and sucking energy out of the cavity. You'll notice that the reflected power goes way down. Why? Because energy is going into the beam. It's not coming back to the source anymore. But the thing is, that gradient is not very flat, which means the beam energy is not going to also be flat. I'm going to start to put an energy spread in the beam, and that's not good. All right, so I got to do something about this. And what you do, oh, and all that power coming back, maybe my generator isn't going to like it. And it may not like it because I wasn't careful to put the half number of wavelengths in, or maybe it could be that I have a situation where I'm broader band, and there is no such thing as half number of wavelengths, and my generator can't take it. So you pop Mr. Circulator in there, that gives you the isolation to where the generator is always happy. That's why we have circulators. And then we have to worry about this thing called beam loading, and that's where Mr. Low Level comes in, which you can use feedback and feed forward. You know exactly when the beam's going to show up. I mean, you're in a very well-timed system, so you know it's going to come, and you can sit there, and we did this certainly in our Linac as well, is you can adjust when to turn on the feedback, feed forward pulse, so that you can time it perfectly to minimize the blips that will occur. And this makes the gradient flat, and yes, it makes the phase flat as well. And what it means is now you have to put in more energy into the cavity than you were. So how am I going to pick that power source to do that? I do not want to be reaching gradient with saturated power, because now when the beam comes across, I got nothing more to give. Okay? And I don't want to go to saturated power when I've got to give it more power. So that's a factor of about almost 6 dB from where you get to the gradient in idling, and then when the beam shows up, I got to put in 4 times the power in order to do it. And that's all dependent on beam current, of course. But if you don't do it, you will not have an energy flat beam. And you know, low-level RF systems got lots of digital stuff in them these days, but it's only because of digital stuff that you could do the feed forward and all this other really sneaky fun stuff. And here's the former control room at the main injector Tevatron. Most of the stuff in all these racks is lots of low-level RF hardware with signal generators, fan out to go into multiple cavities, feedback, feed forward, lots of stuff. And then there's just one more thing, is something called higher order modes. Okay, is if you're listening to a violin does not play a single tone. If it did, every instrument would be absolutely boring. Every instrument sounds different because of the harmonic content it makes. So it may be sitting there vibrating with the fundamental mode, and then there's a second order mode, and then et cetera, all because it's a fixed point here and a fixed point there, but that string can vibrate in many modes, and it's that makes the sound rich. Piano will look exactly different. They can all play the same note, and when the conductor says, you hear this cacophony, they're all playing the same note, but the harmonic richness is incredible. That's higher order modes. Okay, well, the beam plucks the cavity as well, because the beam is ideally, if there was just one particle in there, it's like a delta function, which means it can have very harmonically rich characteristics. And when you have lots of beam, you have lots of little independent delta functions, but they're controlled typically by the RF system that's keeping them at a certain frequency. So the thing is, what can happen is that you can now start modes up in one of these cavities, especially superconducting cavities, and the thing is, they're going to add to the voltage in a way maybe you don't like. Well, maybe you don't like. The beam certainly doesn't like it. And depends on how much beam current you have as to how terrible the higher order modes are. Some of the machines that are being designed now are excluding higher order modes because there's, through lots of modeling, it shows that the higher order mode effects may not cause the beam to go unstable. All right? But other systems, they have to worry about it. The bad thing about a higher mode coupler is it's yet another hole into the vacuum system, and it's meant to suck power out at these harmonics. and that's a source of heat, and it's a source of heat load, so it's cumbersome toward the cryogenic aspect of things, and it's cumbersome if they start to get so hot because of whatever mode there is that they become impossible to run the cabin. Higher order mode dampers are a controversial subject, and for instance, they had them built in to SNS here, and because they thought they would need them, but as it turned out, after years of operation, they were kind of a headache. They pulled them out. Okay, and you know, and doing that is more expensive than knowing whether you needed them in the beginning or not. But are you guys putting higher modes in, Dave? They're not doing it. They have a pretty broad bandwidth. And
we made the I mentioned this yesterday, we made a specification that all our higher order loads have to sit 5 megawatt hertz away from our beam lines, our beam machine lines. And our first cavity comes up and the higher order loads right on.
and you guys are going to test every cavity too, right?
This tells you got to really pay attention to,
Yeah.
to the manufacturing, because just a simple misshape in the cells push the higher order loads right into the machine lines.
Okay, so this is something that I got from Chris Adamson a while back, is sure you'd like to have as high a Q as possible, but at some point, whether it's the quality assurance point of things, there's a dollar cost in it. So they used to think the theoretical gradient was about 40 megavolts per meter. That's not necessarily very true. But what you can see right here is the relative cost has got a rather steep slope between an ideal and something that starts to be commensurate with copper, for instance. And so the reason why there's 31 megavolts per meter accelerating gradient, but you'd like to test it out to 35, which is what they're doing in many 1.3 gigahertz systems, is because of trying to stay as low on this cost curve as possible. And there's people that want to cut costs by saying, let's just test every 10th guy. Now, the reason that wouldn't be such a bad thing if you were driving each one of the cavities independently with my magnetron, because then if one fails, it's okay. But if I wanted to drive 3 cavities with 24 cryo modules with them from one power source, because, quote, that looks to be the cheapest way of doing it, if I have one bad apple in the basket, I cannot drive the rest of the basket above the bad apple. And now you spent an enormous amount of time and money to get this high gradient, but you have been shackled by someone who didn't quite make the grade. So that's why it's always nicer to have an individual power source per cavity, because, okay, especially with an electron machine, the beam's relativistic, so you don't have to worry about the phase velocity changing if I don't have enough gradient. It just gives it a small push instead of a big push, but it still gives it a push. And the thing is, where until I can make this magnetron thing work, well, it works already, but until I make something that says, see, here's one that works at the real McCoy frequency and power level, that's what some people need to convince you. But you really want an IR source per cavity, and that's what SLAC is doing on LCLS too. It's going to be solid state. So if this cavity is half as good as that one, it's okay. Okay, we'll just drive it at half, but the rest of the cryo module gets whatever it can take, and you have that flexibility. But that does cost more money to do that. Okay. And there's all kinds of topologies. You could have the klystrons on top, and you got the beam down the bottom. Tesla's got the beam much deeper, but they still want to put the modulators on top and feed the klystrons in the tunnel. They only have one tunnel. Then you can have, you can have 2 tunnels side by side, which is what they were initially planning for the ILC. One tunnel would have, because they want the ILC to be plenty deep, and you could have a tunnel for machines and beam and klystron in the other. I believe the latest design for Japan is still 1 tunnel for the ILC, just because that saves an enormous amount of civil construction costs. So then the whole thing comes together, and you've got all these cryo modules, piezo tuners, low-level RF, master oscillator, which you have to distribute for kilometers to keep everybody happy in phase. And when you distribute it, you got to make sure it's thermally protected so that the phase doesn't change between summer and winter or night and day. That's a whole other topic in itself. And then the very last thing here is crab cavities, which have only been successfully implemented at an accelerator in Japan. They were on the docks to be done at LHC, is because when you have a colliding beam facility and you have 2 rings, and in the case of the LHC, the rings are side by side. And so that says they actually crisscross, I think, 8 times. because of course if they didn't, then the revolution frequencies of the two beams would not be the same, and the chances of them meeting inside of your detector is 0. So, but a crab, so now at some point you've got some slight angle where these guys are crisscrossing. And if you can imagine, two things going through each other, is the cross-section of this is much shorter than the cross-section of the going head-on. So a crab cavity is a single pass, tilt me just a little bit so that you can see what this thing did. So it goes through the cavity, starts to tilt, so that when they finally get to the collision point, you're getting more of a collision point. They're extremely expensive to do because you need quite a bit of voltage. You got to do it all in one pass, and then typically there will be anti-crab cavities to push the beam back to its normal orbit someplace else. I know one of our former students, Ram Kalaga, he was working on this, and I don't know what the latest status is of crab cavities at LHC, but it's really expensive, and I'm not sure if they're pursuing it much further. Okay, and so now let's take a look at overall what does it take to make something happen. So you got to get your energy out of the wall here someplace. You got to convert the AC power to DC power. You got to turn it into RF power. You got to get the RF power down to the cavity, and you got to take all these things and multiply them to each other. With the current technology, you're at best going to get 37 to 48% efficient. That's just the RF. If it's superconducting, it takes a lot of energy to make something cold. And so getting more than 10 or 15% of energy into the beam is a real challenge. And in many accelerators, like PIP2 that we're designing, if we build it as it's being designed, it will be the most inefficient accelerator ever. And there's a bunch of us that can't believe we're pursuing it, but I work on it nonetheless. Okay, so talking about cost one last time here is the cost of RF power, AC to DC conversion, everything else. It can be 25 cents a watt for a multi-beam klystron driving lots of things, but has lots of pejorative aspects to that, better than the worst cavity. And it makes your distribution system really expensive. And it can be $15 a watt. And $15 a watt, maybe more than that. And the cost estimates for an accelerator on the design tables right now approaches 1/3 of the cost of building an accelerator. So people pay attention. And if you can save money yet provide reliability and efficiency, that's a prominent point that even the most clouded managers have got to sit up and listen to. So that's it for lectures. To take a break. From this point on, it's all fun and games. What I'm going to do is see if I can figure out how Mr. Fancy Pants here works. I know how it works in generic mode, but Mr. Fancy Pants has impressed me, and I'll be damned if it's going to not let me do it. Sure, yeah. Also, I can send it to everybody.
Yeah. So Ralph just showed Chris Adelson